Hello, welcome to the channel of Namagiri Academy. This is a video um, on differentiability, and in this video, we shall discuss constraint optimization. We have already seen wo- unconstrained optimization of functions of real valued functions of more than one variable. That means if f is suppose a function of two variables, here in this example, um, real value, then suppose if we want to find the maximum and minimum of f, then what do we do? First thing is that um, we first find out the values of x and y, the points x comma y, uh, at which uh, which must satisfy a certain condition, so that f may take a minimum or maximum value at that point, so that these are necessary conditions. These conditions must be satisfied by points. So these are, that is, fx at x comma y must be equal to 0, and also so this is the first order derivative of f with respect to x, and this is the first order derivative of f with respect to y. Both must be equal to 0. First we solve these two equations. Okay, so that gives us a certain list of points. Now so this actually restricts our search to only a small set of points, because there will not be too many points which satisfy this condition. So typically we get only a handful of points which satisfy this condition. So that tells us that only at some of these points we shall get either minimum or maximum. Now in order to check at which point we get minimum and at which points among all these we get maximum, we check the second condition, that is the sufficient condition. If a point satisfies sufficient condition for maximum, then f attains maximum at that point, and if it satisfies condition for minimum, then it attains minimum at that point. And there may be points that neither attain minimum nor attain maximum. Those at those points, these are saddle points. So points which satisfy these two conditions are called critical points. The sufficient condition, for getting sufficient condition, we first define a quantity which we often called it's often denoted as d, and it is defined as f. This sufficient condition is defined in terms of the second order derivatives, minus fxy the square. Now this is for every critical point, we compute this quantity. Okay, for we find out fxx, fyy and fxy. We substitute the values of x and y in this expression for every critical point, and we compute this quantity d for that point. If it turns out to be greater than 0, and also if we have fxx greater than 0, then I think it means that the at that point f attains minimum. If this is greater than 0 but fxx is less than 0, then it means that it is maximum. I am not very sure whether this is minimum and this is maximum, or it is the other way around, but right, that is not so you can just cross check. If d is less than 0, then this critical point is neither minimum nor maximum. It is something called as the saddle point. We have discussed these things earlier. And if d is equal to 0, then the test is inconclusive. It doesn't tell us what the point is. Inconclusive. So now this is about the unconstrained optimization, in the sense that here we are considering the whole domain where the function f is defined, and over the whole domain we are checking whether checking at which points f is taking minimum and maximum, and where it is saddle point. Now here I must mention that when we say that at a certain point f takes a minimum, we only mean that it takes it's a local minimum. Okay, it may not be the global minimum. Right? So these minimum, maximum and saddle points mean that they are local. Okay, fine. Okay, so now this means that this we are not sort of putting any restriction on the values of x and y, or rather we are not subjecting x and y to any conditions. Sometimes we need to check for which we want to check the minimum and maximum of f such that the points x, y satisfy certain condition. So that is called as constraint optimization. So in that case we are not taking into consideration the whole domain where f is defined. We are only taking into consideration only those points x comma y which satisfy that certain condition, and over that set we check at which points in that set f takes minimum and maximum. And since we are putting a constraint on the set of x and y, this is called as the constraint optimization. So we want to minimize or maximize depending on as the case may be f x y subject to the constraint g of x comma y equal to constant k. So we are not now taking the set of all x y over which the function f is defined. We are only taking into consideration only those x comma y for which g of xy is equal to k, and among all these x comma y, the points x comma y, we shall see for for which x comma y f takes maximum, and for which x comma y f takes minimum. That is our question. So now our previous technique will not work, because this technique is tells us this technique takes into account the whole domain. Alright, so now what should we do? So this can be solved using the method of Lagrange's multiplier. What the method is: what we do is we solve the following two equations. Now the proof of this is beyond the scope of our syllabus, so we shall not discuss that. In the case of unconstrained optimization, in this previous case, we solved the equation fx equal to 0 and fy equal to 0, and that gave us the values of x comma y, and we called them critical points. So now in this case we shall not solve these two equations, we shall solve two other equations. What are those equations? We shall solve first equation, fx equal to lambda gx, where gx also is the first order derivative of g with respect to x. The second equation that we shall solve is fy is equal to lambda gy. So we shall find out for which points x comma y this fx is a linear multiple of gx, and fy is the same linear multiple of gy. So if we denote this fx comma fy this vector fx comma fy as the gradient of f. This is the standard notation of gradient. Then this means gradient of f is actually equal to lambda gradient of g. So we are in fact trying to solve these two equations, but observe that these are equations in x, y and lambda. Okay, but so we have three variables, but we have only two equations here. Okay, so solving these two, generally we should have as many equations as we have variables. So we must have the third equation in order to solve this system, but the third equation is given by this x comma y also should satisfy this equation g of xy equal to k, and that gives us the third equation. So this equation fx equal to lambda gx, fy equal to lambda gy combined with g of x comma y equal to k gives us three equations in three unknowns, and by solving them we get the values of x, y, and also we get the value of lambda. The value of lambda is practically of no use. Although we get that value, it is not of any direct use to us, but using the value of lambda we shall find the values of x and y, And once we find the values of x, we shall get a set of values of x and y, and among from that set of x and y we shall find out at which for which x comma y the f takes value f takes maximum and f takes minimum. Okay, so let us take an example. Okay, find the minimum. So there is yet another thing, that this is for the functions of two variables. We can extend this to the functions of three variables, and also in general to the functions of n variables. So if suppose we have a function of three variables, x comma y comma z, real valued function, again that needless to be said, real valued function, and if we want to minimize or maximize f subject to g of, now we shall have g x y z equal to k, then now we shall have to solve gradient of f is equal to lambda gradient of g, gradient of g, which means fx equal to lambda gx, fy equal to lambda gy, and fz equal to lambda gz. Again we have here three equations, but we have four unknowns, x, y, z and lambda, but these three equations along with g of x, y, z equal to k gives us four equations. So our job is done. We have four equations and four unknowns. We can solve all of them. That will give us various points x comma y comma z, and among those points we have to find out at which points f takes minimum and which other points f takes maximum. That we shall have to check by taking each point individually. Okay, fine. So let us take one example. Use Lagrange's multiplier. So find minimum and maximum of f of x comma y comma z equal to x square plus y square plus z square, subject to the constraint g of constraint, let's say x plus y plus z equal to 3. Okay, so now here f is x f of x comma y comma z is x square plus y square plus z square, and g of x comma y comma z is equal to x plus y plus z. Okay, our form of g x y z is this is g of x comma y comma z equal to 12. Here k is equal to 12. All right, so fx is equal to 2 times x, fy is equal to 2 times y, fz is equal to 2 times z, gx is equal to 1, gy is equal to 1, gz is equal to 1. So fx equal to lambda gx. If suppose we do that, then what we get is 2 times x is equal to lambda times gx, which means lambda. Similarly, fy equal to lambda times gy gives us 2y equal to 2y equal to lambda times gy means lambda, and fz is equal to lambda times gz means 2 times z is equal to lambda. All right. Okay, so this 2 times x equal to lambda means x equal to lambda over 2. Similarly, 2y equal to lambda means y is equal to lambda over 2, and 2z equal to lambda means lambda equal to z over 2. Now we have expressed x, y and z in terms of lambda, or other way around you can say. So now here this definition of g will will start playing its role. Here we have g of x comma y comma z is equal to x plus y plus z, which is equal to 12, and we have found out sorry, here I should write z is equal to lambda over 2. We can substitute these values. X is equal to lambda over 2, so x is equal to lambda over 2 plus y is equal to lambda over 2. So x plus y plus z, z is also equal to lambda over 2, is equal to 12, because g of x comma y comma z is 12, which is x plus y plus z is equal to 12. So this means 3 times lambda over 2 is equal to 12, meaning that lambda is equal to 8. So look that we have found the value of lambda here. So out of the four unknowns x, y, z and lambda, we got the value of one unknown lambda, but as soon as we get the value of lambda, the values of all other variables can be easily found out, because each of these is expressed in terms of lambda. Now, x is lambda over 2, means 8 over 2, which is 4. Y is also 4, z is also 4. So this is the only point that we have got. Here we haven't obtained more than one point. So x comma y comma z equal to 4 comma 4 comma 4. Is the point that we have obtained. So what is the we want to find out the minimum and maximum of f, that is x square plus y square plus z square. So this is since x, y and z are all three equal, this is 3 times 4 the square, which is 48. Now is this 48 the minimum or maximum? That is our question. Observe that, so this is either minimum or it is maximum. Now suppose x plus y plus z equal to 12 is something that is our equation. Suppose we set both x and y equal to 0, then z becomes equal to 12, and if z is equal to 12, then for this tuple 0 0 12, x square plus y square plus z square becomes equal to 0 square plus 0 square plus 12 square, which is 144. So f takes value 144 when x is equal to 0, y equal to 0 and z is equal to 12. Observe that 0 0 12 also satisfies this condition. So therefore certainly for x equal to for x, y, z equal to 0 0 12, f of x, y, z equal to 0 square plus 0 square plus 12 square which is equal to 144. So this is certainly not the maximum value. Okay, so this is and hence minimum. So f the maximum, sorry, the minimum of f is equal to 48 and maximum is equal to 144. So these are the minimum and maximum of f. Alright, so this is how we find out. So actually, to find out the maximum of f, so we didn't get the value of maximum by Lagrange's multiplier, we only got the value of minimum by Lagrange's multiplier. So whenever such things happen, so this is because these conditions actually only give us the local minimum or local maximum, and whenever we fail to get whenever there is no local minimum or local maximum, we must look at the boundary conditions. So this is a boundary condition. By setting x and y equal to 0 and only taking the maximum value of z equal to 12, setting the maximum value of z equal to 12, we are actually taking the boundary condition, and that boundary condition gives us the maximum. Okay, alright, let's take one more example. Find three real numbers this is not really not quite. Let us take different example, because that example will be similar to the previous one. I am referring to the exercises given in the our SYBSC notes. Okay, so let us take this one. Find the points on this sphere. X square plus y square plus z square equal to 25, that are such that x plus 2y plus 3z, this function takes minimum and maximum. So for what are the points on this sphere such that this function takes minimum and maximum? So our f here, f of x comma y comma z is equal to x plus 2y plus 3z, and we are restricting the set of points under consideration to this sphere. So our g of x comma y comma z is equal to x square plus y square plus z square equal to 25. So k is 25 over here. So fx equal to lambda gx gives us here differentiating f with respect to x gives us 1 equal to 2 times x, because sorry lambda 2 lambda x, and derivative of g with respect to x is 2x, so 2 lambda x fy. So we can write, eventually we shall need this to be written in terms of fy equal to lambda gy is 2 equal to 2 times lambda y, which means y is equal to 1 over lambda. Fz equal to lambda gz means 3 equal to 2 lambda z, which means z is equal to 3 over 2 lambda. Now we have got the values of, there are expressions for x, y and z in terms of lambda, and our now we shall use again the constraint here to solve for x, to solve for the value of lambda, because always remember finally we shall have to fall back to our constraint condition, substitute for x, y and z in the constraint, and then see what we get, what value of lambda we get. So constraint is x square plus y square plus z square equal to 25. Now substitute here for x, y and z, so we get here 1 over 4 lambda square plus 1 over lambda square plus 9 over 4 lambda square equal to 25. Now solving, we get here we should multiply by 4 denominator as well as numerator, then we get 14 is equal to, and we shall multiply both sides by 4 lambda square, so 25 multiplied by 4 lambda square. I hope it is clear. So lambda square is equal to 14 over 100. So this means lambda is equal to plus minus square root of 14 over 10. Okay, so now we have obtained two values of lambda, so we shall have two values of x two values of y and two values of z. So x is equal to 1 over 2 lambda, so that means plus minus 10 over 2 times root 14, which means plus minus 5 over square root 14. Y is equal to 1 over lambda, so that is plus or minus 10 over square root of 14. Z is equal to 3 over 2 lambda, so that is 3 multiplied by 10 plus or minus 2 times square root 14, which is equal to plus or minus 15 over square root of 14. So these are all possible values of x, y and z. Now we get various combinations of the points. So in fact, since we have got two possibilities for each of x, y and z, the total number of points that we get are is 8. Okay, so because two possibilities for x multiplied by two possibilities for y multiplied by two possibilities for z, meaning that we actually get 8 possible points by considering each possibility of x, y and z. So for which of these 8 points does our function f takes maximum and which point f takes minimum? Observe that f is a sum of these three terms, x plus 2y plus 3z. So now when all three x, y and z are positive, f will take maximum obviously, and when all three are negative, f will take minimum. So therefore whenever all three x, y and z, so when x is equal to plus 5 over root 14, y is equal to 10 over root 14, and z is equal to plus 15 over root 14, f will take maximum, and when each of these is negative, negative 5 over root 14, negative 10 over root 14 and negative 15 over root 14, f will take minimum. And you can actually find out the values, the minimum and maximum values of f by substituting here the values of x, y and z in the expression for x. So in this way we solve these problems of constraint optimization using Lagrange's multiplier. I hope it is clear to you, and if that is clear, then we shall stop here. That completes our topic on constraint optimization. Alright, bye.